Let f and f prime be differentiable functions. Values of f and f prime are given. Let n equals the integral from 0 to x squared of f prime. Evaluate n of 3 and n prime of 3. So let's see if we can set each of these up. So, I mean, we do have a f prime table of values, but normally we want to be able to look at a graph and look at the area. So it looks like the f prime table is not maybe not where we need to be. Maybe we have to take the antiderivative because we do have something at the f of x level. So maybe we can do this. We know the integral of f prime is going to make it rise up to f. So this can be f of 9 minus f of 0. I mean, if we had an f prime graph in front of us and there were geometric shapes, we could add up those areas, but we have something at the f level, so we can just make it rise up to take the antiderivative, apply first theorem, and then f of 9 minus f of 0, we can do that, right? So -2 minus 5. Next part, evaluate n prime of 3. N prime of 3 is the derivative of this. So let's find the derivative of this before we plug in 3. So here's my n of x again, from 0 to x squared of f prime. So n prime would be the derivative of this. So the derivative of the integral. Okay, so this should remind us of second theorem. We know that these two operations cancel each other out. So n prime, we're just going to plug the upper bound into the variable. Technically, these should be t's here, so x should be plugged into t, but it's okay. X squared in for f prime, so it's f prime of x squared, but times, what do we also need to include here? Times what? X squared becomes 2x, yeah. So remember, second theorem. A lot of times we ignore that upper bound because it's just x, and x's derivative is times 1, so nothing really impacts. But here there's x squared, so with second theorem, we cancel these out, we plug the upper bound in, and then we multiply by the upper bound's derivative. Okay, so now we can use this to find n prime of 3. Three squared is 9. 2 times 3 is 6, so we should need to do f prime of 9 times 6. Look at our table of values. F prime of 9 is -4. So -4 times 6 is -24. Part J, let Q equals natural log of f of x, find Q prime of 5. So the hint is there's chain rule. And then also as a reminder, we know the derivative of natural log of u is u prime over u. Okay, so try that. Show the derivative first before you do anything with the 5. Okay, so u prime over u, my u value is just that f of x stored inside natural log. So u prime over u, so it's f prime over f. It'll stay in function notation here. Replace all the x's with 5. So f prime of 5, we go to our table. F prime of 5 is 6. F of 5 is 4. So 6 over 4. Next up, f of natural log of x, find r prime of 1. We're going to find the derivative. There's a little bit of chain rule first. Outside times inside derivative. So outside derivative is f becomes f prime. We keep everything inside the same. Now we're ready for the inside derivative. So natural log of x's derivative is just 1 over x, right? U prime over u. Okay, replace every x with 1 and see if we can get it down to a number. So natural log of 1, we can actually evaluate that. Natural log of 1 is 0. So f prime of 0 times 1. We know f prime of 0. Table gives us -3. Okay, page 17. The function f is continuous, consists of 3 line segments, 1, 2, 3, and a semicircle. The function g is defined as the integral from -2 to x squared of f of t. Find g of 2, g prime and g double prime. So you know with this setup, it's involving either the area, the order pair, or the slope. So let me build all the functions that we need to use. Oh, this was a little bit more complicated here. So let's see. G prime is the derivative of this. And again, we know this these operations cancel each other out. Upper bounding for the t, we get f of x squared times 2x. So this is a little bit more involved because that x squared is not going away. It's times 2x, which means that if I want to find the derivative again, g double prime, I got to go through a little bit more involvement to build a derivative. I got to do chain rule and product rule as well. So let me build that out. So anytime I have 2 variables multiplied or 2 expressions multiplied, I got to go through product rule. Okay, so f of x squared becomes f prime of x squared times 2x. There's an outside and inside portion, so we take turns with each derivative. F's derivative is f prime, x squared's derivative is 2x, but we got to make sure that we don't just put the 2x inside the parentheses. We got to, when we do chain rule, it's outside's derivative, keep the inside the same, and then multiply by the inside's derivative. And then g prime 2x becomes 2. Everything that we need is in front of us. Let's go ahead and find g of 2, g prime of 2, and g double prime of 2. Now we're just plugging in. So we're doing displacement here from -2 to 4. So we'll add up the area of this semicircle, triangle. That should be all we need for this one there. Semicircle is 1/2 pi r squared. Triangle here, 1/2 base times height. So 2 pi plus 2. Everything's above the x-axis, so semicircle is 2 pi, and the triangle is 2. G prime of 2. So f of 4 times 4. I'm just plugging in, replacing all the x's with 2. Table of values, f of 4. Well, actually, we can look at our graph here. F of 4. This is the f graph, so f of 4 is 0. So 0 times 4 is going to be 0. Okay, g double prime of 2, replace every x with 2. F prime of 4, that's the slope of the f graph at 4. So the slope of the f graph at 4, this is part of a negative slope here. I go down 2 over 1. the slope of this line segment is -2. And f of 4 is still 0. 0 times 2 is still 0. So -32 plus 0 is -32. Next up, find h prime of 3. This is a function within a function. We got to go through chain rule, but one is in function notation, the other is not, but we can still go through chain rule. Outside's derivative, then times inside's derivative. Let's find h prime of x first. Make sure when you go through chain rule that when you take the outside's derivative, that you're not changing the inside, you're copying the inside down as part of your outside derivative. And once that's done, then you can move into a separate space and find the derivative of the inside portion. Okay. Now we can plug in the 3. 15 minus 9 is 6. F prime of 6, we go to our graph. That's the slope of this line segment, which is 1, up 1 over 1. Okay, we'll come back to AB3 the next part in a little bit. Let me go to the next page, page 18. And let's practice going through extreme value theorem, which is finding max and min. Okay, so we have a portion of f prime that's given to us here. Twice differentiable, meaning it's a smooth curve all the way through. Okay, determine relative max, relative min. Let's just create a slope sign line. I really want us to get to part 2, but before we do that, let's just create a slope sign line so we can actually find our critical points. So I'm going to create my slope sign line here. I know my endpoints, -3 and 8. This is my derivative graph, so I want to label accordingly. Above is positive slope, below is negative slope. On the x-axis is slope 0. Critical points are my x-intercepts, so 1 and 6. Between -3 and positive 1, above the x-axis, so positive slope. Between 1 and 6, below the x-axis, negative slope. Between 6 and 8, above the x-axis, positive slope. Find the minimum value. So if you see the word minimum, this is the understood is that it's absolute minimum. So we're doing extreme value theorem, which means test endpoints and critical points. But do we need to test both the 1 and 6 if we're just looking for the absolute minimum? Which one do we not need to test? 1. If you tested 1, it's not wrong. It's just you're just doing additional work. You know that a relative maximum is never going to be the absolute minimum, right? The hill of a graph is never going to be the lowest point on the graph. So we can ignore the -1. Just test -3, 6, and 8. Now, notice that this problem doesn't give you an integral formula like this one, where you can just plug in and find that area. So if the problem gives you just a starting point, then we have to use that formula, final equals initial plus displacement. So we're going to use this formula here. Okay, final equals initial plus displacement. And we'll do that for each of the 3 points, -3, 6, and 8. So let's find f of -3. F of -3, we have to use our anchor point as our starting point. So we need to start at f of 1. And then we have to bridge the gap from 1 to -3. Sometimes you may be going backwards, but it's okay. You always want to make sure that you start lower bound here and you end upper bound here. So once you set up following the formula and then you realize that the bounds are out of order, then you can swap the bounds. Okay. And if I swap the bounds, I can change this to a what? What adjustment do we need to make if we switch the bounds? Negative, yeah. So f of -3 is equal to f of 1 minus integral from -3 to 1. And the reason that we want to swap the bounds is because we want to read the graph the way it is. Otherwise, you have to adjust and think, oh, this is now positive and this is negative if you're reading backwards. I think it's easier to just read forwards and then adjust the bounds so that we can do that. So from -3 to 1, that's nice. They tell us the area there, which is 10, and it's above the x-axis, so we want to keep that as a positive 10. And f of 1 is -2, so therefore it's -2 minus 10. The minus is because we adjusted the bounds. So -2 minus 10 is -12, so that's one candidate. We can skip over 1. We can go to 6. So f of 6 final equals initial plus displacement. My initial again is at f of 1. This time I'm going from 1 to 6. No need to adjust the bounds because my bounds are already in the order that I needed it. So f of 1 again is -2. And then from 1 to 6, below the x-axis, they tell us the area, but we know the displacement is negative, so -14, which is -16. Finally, f of 8 is f of 1 plus the integral from 1 to 8 of f prime. F of 1 again is -2. And then we just add up the areas here. -14 plus 6 is -8. -8 minus 2 is -10. So between these three values, we're looking for the lowest y value. The minimum value between these three candidates is -16. So absolute minimum is -16. Okay, I'm going to leave the rest of the page and the rest of page 17 for homework. But if I just want to make some progress with our review. So I want to continue with continuity. We can turn to page 4 in the other packet. Okay, page 4. We talked about at the end of class yesterday continuity conditions. So again, page 2 has continuity conditions spelled out. What is required for a function to be continuous at a point? It needs to meet these 3 criteria. Is the point defined? Is the limit defined? And then thirdly, does the point live where the limit lives? Are they in agreement with each other? And so here's page 4. Number 5. Let f be the function given. Which of the following statements must be true? Right now, it's not so obvious as to what's happening here. So anytime I see anything with continuity, I'm just going to go through my conditions and see if I can step through my continuity conditions and see if I can get this to at least show that once I step through it, then I can kind of go back and decide which one I want to keep. Okay, we know that the point in question is at 3, so all these are at 3. So first is, let's find f of 3. Let's just see what's going on with this function. We see that 3 is defined with the first piecewise, so plug 3 in for x. So 3 plus 2 is 5, so there's my point. Second, limits. I want to find the limit as x approaches 3, but you see that this piecewise has two functions split on either side of 3, so I need to do one side of limit. I need to do approaching 3 from the left and also approaching 3 from the right. Let's see what each of them give us. Basically, this is like what we're doing on the graph, drawing the arrows and seeing the arrows are actually meeting, moving towards the same y value. So 3 plus 2 is 5. The left arrow is headed towards 5. The right arrow is also headed towards 5. 12 minus 7 is 5. So limit exists. And the third condition, is the third condition going to pass? Is the point and limit at the same location? Order pair is 5, limit is 5. Do they agree? Yes. So third condition also passes. F of 3 lives where the limit lives. So we've confirmed that the graph is continuous at x equals 3. Limit exists as well, so that checks off because we're able to show that was the case. Differentiable is asking about slope. Is the slope going to be in agreement? So let's do this. Let's find the derivative and see if we get the same slope. So f prime for this graph, what's the slope of this? What's the derivative of this graph here? Just what? 1. So the slope is 1. And here, what's the derivative? 4. So is this function going to be differentiable? Are they going to share the same slope at 3? No, right? You have a slope that is 1, and all of a sudden it jumps to 4. So that's a sharp turn. The slope doesn't exist at that point because there's a sudden change. So this is considered not differentiable because you have a sharp turn, right? Or a sudden change, not a smooth transition. So therefore, continuous and limits exist, but not differentiable. Okay, number 6. Let g be the function defined for what value is of k is the function continuous at x equals -3. So whenever I try to solve for k and I see the word continuity, I'm just going to step through my continuity conditions. The conditions gives me a way to kind of walk through my problem. Right? And then once I walk through it using continuity conditions, it should be obvious what the k value is going to be. All right, so first condition, does a point exist? We know that the value is at -3. I want to plug -3 into one of these. I know that -3 doesn't exist with this one, but it does exist here. So f of -3 equals k. We're not able to find any progress, but at least we're just kind of walking through our conditions here. F of -3 equals k. Okay, we'll keep going. Second condition, does the limit exist? Now, this is not split on either side of -3. Okay, it's not like the previous one where you have less than and greater than. You have two different graphs on either side. This one is saying everything is stored here except at a single point, which is elsewhere. So here we can just rely on the limit. This means everywhere except -3. So to the left of -3 is this function. To the right of -3 is also this function. We can do one-sided limit, but there's no need to since we're talking about the same function. So whenever you see it doesn't equal to and equal to, that just means your graph is mainly where that doesn't equal to because it's everywhere except at this point. So all we need is one limit statement. Okay, so we got to do this algebraically, right? What's the first step? Again, yeah, see what happens. So -3, 3 squared is 9. 9 minus 9 is 0. -3 plus 4 is -12. -12 plus 12 is 0. So 0 over 0, what can we do? Can we say that the limit doesn't exist? What's happening here? There's a what here? Oh, yeah, so we got to keep going, right? Either you factor, or I think we probably prefer L'Hopital's rule. So you can find the derivative, do L'Hopital's rule. Reevaluate, we get -6 over 4, which is -3 halves. So the limit is -3 halves. We keep going. Third condition. Do they agree? Well, we're trying to solve for k so that the function is continuous. So the function is going to be continuous. These have to agree, which means k must be equal to -3 halves. So we're able to solve for k without really trying because we're just walking through our conditions. Okay, try number 7. Number 7, follow your steps. Direct substitution first, see where that takes you. Okay, direct substitution should take you to 0 over 0. And we know that we can't really, it's hard to factor, right? So go into L'Hopital's rule. I just want to kind of go through one thing before you try it here. What's the derivative of pi squared? 0, okay? Why is it not 2 pi? Why can I not do that with like an x squared? Which is a constant, right? Yeah, so I know that pi is a symbol, but we don't do power rule like we do with x squared. Pi squared doesn't become 2 pi. Pi squared is a number. That number will go to 0. Okay. All right, so go through L'Hopital's rule. Once you build the derivatives from top and bottom, you can replace all the x's with pi, and that should take you to something other than 0, 0. It should resolve itself and get you a real number. Hey, cosine's derivative is negative sine. Sine of 2x is cosine of 2x times 2, and 1 goes to 0. X squared becomes 2x, pi squared becomes 0. Now that you have your derivative, replace every x with pi. Use your unit circle knowledge. Sine of pi is 0. Cosine 2 pi is 1. 2 times 1 is 2. So 2 over 2 pi is 1 over pi, because the 2's cancel out. Okay, your homework is to finish up page 16 through 18 from the previous AP packet that we did. And then tomorrow we will continue. We'll do a full review, and I'll also have morning review on Friday, and then your test will be on Friday. All right, come get your phones. Okay, thanks. Okay. I think just finish this off, but I'll give you credit.
I just realized that there should be pages in these pages.
Thanks. Okay, great.
Thank you. Wait,
Okay, great. Thank you.
Yeah. Oh, it's like,
I don't know what.